Here. The second lecture of the module is going to be a focus on analytical chemistry. I know it says here for oceanographers, but really this could be analytical chemistry for anyone who conducts research in the ocean atmosphere system. And I'm going to break this into two videos because it's a bit long, so I think it's better digested as two parts. So today we'll start with presenting data, what a certified reference material is and how we use them. Briefly, I'll talk about how to keep a lab notebook, but that'll come a little bit more when we're actually in the lab. How to calculate concentrations, how to make solutions, and how to pipette. And then in the second video, I'll do the calibration curve and estimating uncertainty stuff. So this is a bit of a personal pet peeve, I guess, but it is technically correct. Data should be used in the plural form. What I like to do is substitute in a plural word to see if it still sounds correct. So saying the nitrate data is interesting sounds fine, but if you say the nitrate unicorns is interesting, you can immediately see that it's not quite right. So this is just something to watch out for as we're going to be talking more and more about generating our own data. Okay, significant figures. There's a bunch of rules to significant figures, and the reason I'm bringing this up is because even with me harping on this, every year there's always someone who, you do a calculation using a standard curve to get the concentration of something, and then you just report or spit out whatever it is that Excel or your calculator gives you without any thought as to how well you know that number. And so significant figures really matter, and it's not, I'm going to go through what the various significant figure rules are, but it's more about understanding to what order of magnitude or to what degree can you be confident in a number when you're doing something analytically. So how do significant figures work? I'm assuming you guys are familiar with this concept. So there's a bunch of rules, and I'm going to move on here so you can see examples for each rule. So any non-zero digit is significant. So in the first example here, there's 4 significant figures because there's 4 non-zero digits. If a 0 is located between 2 significant figures, it's significant. Okay, so here we've got 5 significant figures. A 0 to the left of non-zero digits is not significant unless rule 2 applies. So in this case, none of these are significant values. And so this number has 3 significant figures. Any 0 to the right of non-zero digits and to the right of a decimal point is, however, significant. So this is a significant number. The author was not trying to say 34.1, they're saying 34.10. So that is indeed 4 significant digits. And what that 34.10 is suggesting is that it's not 34.9 or 34.11, it's 34.10. Or sorry, 34.09. Because if it was 34.1 without the 0, it would suggest that it could be 34 or 34.2, right? It's very difficult, very different things. The last one is a little bit more challenging. So any 0 to the right of non-zero digits and to the left of a decimal point and not covered by rule 2, which is this 0 here, may or may not be significant. And so in this case, 340, you don't quite know if it's 2 or 3 significant figures. The way to get around that is you can express the number in scientific notation if you really need to be absolutely precise. So you could say 3.40 times 10 to the 2. In this case, now this 0 here is clearly significant. And so you've been able to express that it's actually 3 significant figures. Or you could have expressed it as 3.4 times 10 to the 2. In which case, there's 2 significant figures. So when you're doing calculations, and this is really where it comes in, you should never, never, never round down until the final answer is determined. Okay? So if you're doing this example, 3.026 times 4.7 divided by 7.23, this is your calculator answer with no rounding. Excuse me. This answer you would actually present as 2.0 because you always go with the least number of significant figures. So here 4.7, you've got 4 significant figures here, 2 significant figures here, and 3 here. So you'd present your answer with 2 significant figures. But if you needed to use this number in calculation to keep moving forward with other steps, you would use this number. You don't use 2.0 or you'll make a mistake, right? You shouldn't be rounding that early. Another thing with significant figures, conversion factors are exact numbers, and so they actually have an infinite number of significant figures. So they're exactly 1,000 meters in a kilometer. How many meters are there in 7.3 kilometers? So the answer is there's 7,300 meters. So there's 2 significant figures in this number. There's an infinite number of significant figures here. So you would present it with 2 significant figures. So this being infinite number of significant figures matters, right? Because if you were to just apply the previous rules we've given, you'd actually say that that had 1 significant figure, but that's not true. Another thing that sometimes comes up is logarithms. So if you need to determine the log of a number, let's say you're converting H plus concentrations to pH, what you do here is you express the answer using so that the number of digits in the mantissa of the logarithm, which is this here, is equal to the number of significant figures in the original number. So 2 significant figures, so you get 2 decimal places to the right of the mantissa there. Sorry, blanked for a second. Okay, so moving on to key lab concepts. Analytical chemistry is a wonderful field of science. It's something that is usually done under incredibly controlled conditions, right? The definition of analytical chemistry is essentially that you're doing something in a really prescribed, really controlled manner. Oceanography or earth science or working in the marine atmosphere is probably one of the least controlled environments you will ever encounter. Sample collection is not easy. This is me trying to sample rainwater on a ship. Sample analysis, sometimes if it has to be done at sea or in a small boat, you find yourself floating around on a small rubber duck, holding onto an oxygen sample, trying to pipette reagents into it while not puking on yourself. It doesn't exactly look like this. The other thing is that samples, in an analytical chemistry lab, you make up a solution. If something goes wrong, you just make it up again. But samples in earth science can be replicated very easily. If you make a mistake or you contaminate something during collection or transport, or if they're not stored properly, for example, if you're collecting aerosol samples in the Southern Ocean or over the ice, you can't just say, oops, I messed it all up. Let's go back to the ice, and resample it. That's not how it works. You don't have that opportunity. So it's challenging, and yet nevertheless, we still have the same sort of scientific rationale for wanting to be good analytical chemists, right? We need to be measuring things at the highest resolution, precision, and accuracy as is possible. So we apply basic analytical chemistry methods to everything that we do, starting with the use of certified reference materials. So these are specially prepared samples that contain something that you want to measure, known as an analyte, at a very precise concentration that's been predetermined with a high degree of accuracy and precision. They come with a certificate. They're very expensive. And the certified reference material are prepared in a bunch of different ways so that you can choose one that is as similar as possible to real samples that you're going to analyze in the lab. And these are critical because they're used to ensure the accuracy of results across laboratories. So imagine if you and I both went on a research cruise to the Southern Ocean. We both collected a bunch of seawater and we brought it back to our labs. I brought it back to my lab here at UCT and you brought it back to your lab. Let's say you work at Stellenbosch University in the future. We both make a bunch of measurements of the exact same seawater samples and we get different results. So how do we know which lab is right? Are my data right or are your data right? And what we do, the way we get around that being an issue sort of globally, is the use of certified reference materials. So if I say, well, I ran all my samples and then I ran a CRM, and the certificate on the CRM says it's 10.2 micromolar, And I measured it using my analytical procedures, the same way I measured the samples, and I got a value of 10.19. I would say that my data are pretty good, right? So if you run your samples and you get a different number, or you don't run a CRM, then there's no way of us knowing for comparison. So what you end up doing is both labs run a CRM, and then we can intercalibrate fairly easily. It also allows you to identify and eliminate systematic errors. If you're consistently measuring your CRM at, let's say, 10.7 micromolar, it means you have some sort of contamination in your lab, right? Because you're adding something that isn't actually in the sample. Similarly, if it's just all over the place, you're always getting some random number, it means you've got serious problems in your methods. Okay, the other thing that is really critical are blanks. So these are samples that should have nothing in it that you want to measure, but we subject them to the entire analytical procedure in the same way as real samples. And that's how you would pick up. So if you ran a procedural blank in this example, you would probably find that your procedural blank would have about 0.5 micromolar of whatever you were looking for in it, because something in your procedures has added to this. By running a procedural blank, you can figure this out fairly quickly. The other thing you run always is an instrument blank, and that's if whatever instrument you're using gives you some sort of a signal, even when there's nothing there. In theory, that signal should be 0, but it's not always, and so an instrument blank is one way to get at that. And then when you're doing seawater, you frequently have to calculate for matrix effects. We'll talk about that a tiny bit when we talk about a standard curve, but this is something you'll do practically when you're actually measuring seawater later in the year. You also frequently have field blanks, and we'll talk about that more practically when we're at the Cape Point GAW tower, because I'll have you guys deploy a field blank in addition, and you'll do a procedural blank in addition to doing your sample. Okay, matrix effects, I don't want to spend too much time on, because with the atmospheric analysis, we're fortunate we don't have to worry so much about matrix effects. This is more of an issue with seawater. But essentially the issue is when we're doing an analysis procedure, we usually make standards up with deionized water, which has nothing in it, whereas seawater has a bunch of stuff in it. It's got a relatively high pH, it's got dissolved organic matter, salts, other dissolved substances. It's true that our atmospheric samples have other stuff in them besides the analyte of interest, but because they're not salty, it's not such a big deal. The other thing to keep in mind with analytical procedures is what the limit of detection for a given method is. And this is the lowest concentration level that is statistically different from a blank within some sort of specified level. This matters because obviously in some places, some instances when you're making some sort of a measurement, you need to have some general idea what your concentrations are going to be so you can choose the appropriate method. Some methods, so one example I can give you, we have 2 different ways of measuring total nitrogen in our lab. But one method, the chemical method known as the Knox box, has a much lower limit of detection than our total nitrogen analyzer does. So for different sample types, like for example, if you have really high concentration samples, you can use the TN analyzer. If you have much lower concentration samples, you have to use the Knox box. And so different methods have different pros and cons to them and different limits of detection. So that's some theoretical stuff. Thinking about getting into the lab, more practical stuff. The concentration of a substance is usually what we're after, trying to get at. This is a very general measurement unit that states the amount of solute present in a known amount of solution. This is a general definition of concentration, the amount of solute per amount of solution. And in marine chemistry and the marine atmosphere and oceanography, we use lots of different concentration values. So here are some common concentrations that we used in terms of their units and their symbols. Molarity is probably the most common, capital M, that's moles per liter, moles of solute per liters of solution. We also frequently see parts per million and parts per billion, especially in the atmosphere, where you have grams of solute per grams of solution. And you sometimes, when needing to make up reagents, encounter weight percent and normality. So I want to spend just a couple minutes going through some examples because I think it's worth just doing this a little bit practically, because when you guys get into the lab, you're going to have to do some calculating of concentrations. So in this case, you have a solution of 1.5% weight per volume ammonium nitrate, which contains 1.5 grams of ammonium nitrate in 100 mils of solution. And remember, weight per volume, if you go back, weight to volume percent, grams of solute per 100 mils of solution. So that's here. The other example here is that if you dissolve 0.1 moles of calcium chloride in 1 liter of water, you have a solution of 0.1 moles of calcium and 0.2 moles of chloride, because you've got Cl2 here. You also would say that this is a 0.1 molar solution of sodium chloride, because you have 0.1 moles of sodium chloride in 1 liter of water. Another thing to keep in mind, when using parts per million and parts per billion to express an aqueous solution, that the solution's concentration is different if the density is not 1 gram per mil. And so for anything related to seawater, you have to sort of keep this in mind. An example for converting concentration units. So just the first step is sort of like here, understanding what the unit actually means. But frequently you have to go back and forth between different types of concentration units. So if you have a solution that is 28% weight per weight ammonia, and the density is 0.899 grams per mil, what is the molar concentration of ammonia in that solution? So you have to start by figuring out what exactly does 28 weight per weight percent mean. Well, it means 28 grams of ammonia and 100 grams of solution. Moving to molar concentration, you're going to want to get to something that's moles per liter. So instead of grams of solution, you want liters of solution. So for that, you can use the density, which is here, 0.899 grams per mil. And you don't want to know the grams of ammonia, you want a molar concentration. So you need to go from grams per mole. And to do that, you'll use the molecular weight of the solution here. 17.04 grams per mole is the molecular weight of ammonia. And then because you want it in molar concentration, it's mole per liter. And here it's in mils. So you do your mils per liter conversion. So if you were looking through this and wanting to cancel things out, you would cancel grams of solution with grams of solution, grams of ammonia with grams of ammonia, milliliters with milliliters, and what you're left with is moles per liter, which is exactly what you want in terms of the units. So now you can multiply 28 by 0.899 times 1,000 divided by 100 times 17, and you'll get your answer of 14.8 molar. Almost always when you're doing conversions with units, the density and molecular weight are going to be useful things. The other type of calculation you might do, and not in this module, but you do this later in the marine biogeochemistry module, are stoichiometric calculations, where you have a balanced stoichiometric reaction with moles of reactants and moles of products, like we have here below. In this case, one example we can do is oxalic acid is something measured in atmospheric aerosols all the time. It's the most prevalent dicarboxylic acid because it's a byproduct of lots of atmospheric reactions. And if you have this equation where oxalic acid oxidizes to CO2 in the presence of iron 3, and you can see that the molar ratio of iron to oxalic acid in this reaction is 2 moles of iron to 1 mole of oxalic acid. And so if you had, for example, gone out to Cape Point and collected aerosols, which we'll do, and let's say we weighed them gravimetrically and you have 10.62 grams of aerosol particulate matter, you extract that with a solvent, and you oxidize the sample, and complete oxidation of the oxalic acid required 36.44 mils of a 0.0130 molar iron 3 solution. So based on knowing how much iron it took to oxidize the oxalic acid, you can calculate how much oxalic acid is in your sample. So the first thing you want to do is calculate the moles of iron 3 plus used in the reaction. Right, so you're given the moles per liter, but you need to know the actual moles. So you would start with 0.0130 moles per liter times how many milliliters you used, or liters you used, which is easier, 0.03644 liters. And you can see liters cancels. And your answer here is 4.737 times 10 to the minus 4 moles of iron 3 plus. So that's how many moles you used. Now you know this, the stoichiometric relationship is 1 mole of oxalic acid to 2 moles of iron. So in this case, if you use 4.73 times 10 to the minus 4 moles of iron, it means that you have to divide by 2 to get to how many moles of oxalic acid that you actually oxidized. So that divided by 2 equals 2.368 times 10 to the minus 4 moles of oxalic acid. But you don't want to know the moles of oxalic acid, you want to know the weight percent of oxalic acid in your PM sample. So in this case, because you want to go from moles to weight percent, you need to go from moles to grams. And so the way we go back and forth with moles and grams is to use the molecular weight. So the moles of oxalic acid times the molecular weight of oxalic acid, which is 90 grams per mole, tells you that you have 2.132 times 10 to the minus 2 grams of oxalic acid. And so of those 10.62 grams of PM, you have this number of grams of oxalic acid, which means you have, so this grams of oxalic acid divided by grams of particulate matter times 100, because it's a weight percent. You have 0.201% weight by weight oxalic acid in your sample. So that's sort of an example of how you would go step by step using your concentration information and the relative importance of the different types of concentration units. Okay, some practical things, because you guys are going to be in the lab, not this week, but next week. This is an example of what a balance looks like. This is what we use to measure mass. When you need to make a chemical solution, and you guys will be making stock solutions to do your analyses, you have to first weigh out your chemical. There's analytical balances. They're typically digital and can be very sensitive, depends on what kind of balance you use. We have a precision balance and an analytical balance in the lab. You guys will have no need for the more precise analytical balance. You put a clean and dry container on the balance. This is called a weigh boat. And then you tare it so that it's registering 0 when you have the weigh boat on. And then you add the powder to this container using a little spatula until you record the weight you need. A couple of tips: you never put the metal spatula back into the reagent bottle. You're always trying to protect the reagent bottle. And if you weigh out too much, like let's say you get a clump here, you don't put it back in the bottle. You always put it to waste. Okay, so you're always trying to maintain the integrity of that reagent bottle. When measuring volume, which is another thing you'll have to do, when you're making solutions, especially when you're making something that's moles per liter, you need to know the volume of clean water very precisely. This is a graduated cylinder, which is the simplest way for delivering out a relatively well-known volume of liquid reagent. Only accurate, however, to about plus or minus 1 mil. So what we frequently use instead of graduated cylinders are volumetric pipettes, which we'll teach you how to use in the lab. They provide a very accurate way of delivering a known volume of solution, but that's for small volumes. When you actually want to make like a big 500 mil or liter volume, you use a volumetric flask. And these are hand-blown glass flasks that are designed to contain a very precise volumes. As a result of this, we never put it in the muffle furnace, which you'll hear us talk a lot about, cleaning up and how you do the various cleanup procedures. A lot of glassware goes in the muffle furnace to get clean, but these graduated cylinders can't, because you can't heat them and then expect them to still behave as they are supposed to volumetrically. We use volumetrics to make solutions because volumetric flasks are good for highly accurate known concentrations. So the first thing you do is transfer the reagent to the volumetric flask and add enough solvent to bring the reagent into solution. You continue adding solvent slowly and keep mixing. You adjust the volume to the flask's calibration mark, which you can see, that's that little mark there, that line, using a dropper, and then you invert and shake very carefully. So You have to assume that the glassware is clean, so the cleaning process is important. And you need to fill it exactly to the calibration mark in order for it to be correct. The way to do that is to make sure this calibration mark is with your eye level. You guys can read through this, but the reality is that none of this will really make a ton of sense until you actually get in the lab and start doing it yourself. So to make a stock solution, you weigh out the appropriate portion of a pure solid or the appropriate volume of a pure liquid, and you dilute it to a known volume. If you're aiming for a desired molarity, then you weigh out the appropriate mass, use the molecular weight to determine the appropriate moles, dissolve it in the solvent and bring to the desired volume. If you're aiming for the solute's concentration as a volume percent, you would measure out the appropriate volume of solute and add sufficient solvent to obtain the desired total volume. The first example here would be if you were asked to make a stock solution of 500 milliliters of 0.2 molar sodium hydroxide. So how would you go about doing that? Well, the first thing is you'd say, how do we have sodium hydroxide in the lab? And you'd go looking around and you'd find pellets of sodium hydroxide that were an appropriate purity depending on what you were wanting to do with it. The next thing you do is calculate how many grams of sodium hydroxide are needed. So you know how many moles are needed. But you don't weigh things out in moles, you weigh things out in grams on the balance. So you need to calculate how many grams you need. And then you need to double check that you understand what your concentration you're aiming for. So 0.2 molar is equivalent to 0.2 moles per 1 liter. So what that means is you'd start with your desired molarity, 0.2 moles per 1 liter. In order to know how many grams this is, you would use the molecular weight of sodium hydroxide, which is 40 grams per mole. And then so that cancels your moles. So now you're in grams per 1 liter, but you don't want to make a whole liter of it. You want to make 500 mils of it. So you're going to multiply by 0.5 liters. And so now your liters cancels. And what this tells you, 0.2 times 40 times 0.5 is equal to 4 grams. So in this case, you would weigh out 4 grams of sodium hydroxide. You would put it in a 500 ml volumetric flask, and you would slowly add water until that was completely dissolved, and then you would add water up to the line. And at the end, you would have 500 mils of a 0.2 molar sodium hydroxide solution. The second example is if you were asked to make 2 liters of a 4% volume per volume acetic acid solution. You would start by finding the appropriate concentrated glacial acetic acid in the lab. You'd find this in the acid storage area because acetic acid is an acid. Glacial acetic acid is 99.8% weight per weight acetic acid. You always work with concentrated acids in the fume hood and wearing the appropriate safety attire, which we'll be talking more about safety attire when we're actually in the lab. And then in this case, what you're aiming for, 4% volume per volume is 4 mils of acetic acid and 100 mils of your solvent, in this case water. You need 2 liters of it, which is equivalent to 2,000 mils. So here, if you cross it out, it tells you that you need 80 mils of your glacial acetic acid. And you would dilute this not with 2 liters, because it's weight per weight. You would dilute this with 1,920 milliliters of water, so that you would have total 2 liters, of which 4% is acetic acid. Now, once you have a stock solution, concentrated stock solution, we frequently refer to this as the mother stock, you're going to need a bunch of concentrations of that to make a standard curve. And we do that by diluting the mother stock. The easiest way to do that is C1V1 equals C2V2. In this case, the total amount of solute is the same before and after dilution. Another important note is that this wonderful relationship that you'll use over and over only applies when the concentrations are in terms of volume. You cannot do it if you have mass-based concentrations. You'd have to convert them to volume-based concentrations. So you'll do a bunch of examples with this when we get into the lab. Okay, 2 other things to keep in mind before I wrap this up. You're going to be setting up an analytical run with your samples. You're going to have a bunch of blanks. You're going to have a standard curve that you generate, and then you're going to have your samples. How do you actually go about deciding in what order to run them? Well, this requires some thought about what instruments are being used, the kind of sample and standard integrity that you have, the types of blanks, how much sample volume, how precious they are, the stability of the instrument, the time available, etc. It's not always straightforward. There's no one recipe. It requires some thought by the scientist who's doing the analysis. Typically, but there can be exceptions to these, you run the standards in the order of lowest to highest to avoid carryover. It's also the fastest way to see if you're getting a linear response. Samples should not be analyzed in their experimental order. So if you had a time series or a depth profile, you don't want to analyze them in order. The reason for this is you could have, let's say you were measuring a surface to deep profile. Your instrument could be drifting. And so over time, your sample concentrations are going up. And you might think, oh, cool, that's just what my depth profile is supposed to look like. But if you had analyzed them in completely random order, right, from whatever, and you saw this kind of behavior, then you would know that it was your instrument, because there's no reason that you would have randomly chosen samples in a way where their concentrations would have increased over time. The other thing is that you should always run blanks first. It's nice to know by running your procedural blank, you'll see if some big error has occurred. If there's a bunch of stuff in your procedural blank when you're expecting it to be zero, then you can stop and try to figure out what happened. You should also run them throughout. Helps you get at this issue of drift. In addition to running standards at the beginning, you should run one or two standards throughout just to make sure that nothing has changed. You want to analyze samples in batches. So it would be like procedural blank, my zero, a bunch of standards, my standard curve, and then it's like sample, 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 check standard, blank, sample, 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 sample. The other thing is if you're using a CRM, which is always good practice, you should run that fairly early after your standards. I'd insert that right here, because before you waste these precious samples, you can run the CRM and know if you're getting back the value that you should be getting. A couple of other very general tips. Ammonia is in everything. You guys are going to be measuring ammonium concentration, so it's good for you to know this. It's in cigarette smoke, it's in perfume, it's in Axe body spray. It's also in the atmosphere, so leaving your samples open to the atmosphere and uncapped can lead to contamination and loss, so just a tip. Makes it very difficult to measure. When you thaw a sample, and a lot of times we freeze samples as a method of preservation, always shake them a lot after thawing and thaw completely.